Welcome to this year's Calderon-Zygmunt Calderon Lectures. On this occasion, we commemorate the work of Alberto Calderon and Anthony Zygmunt and the very influential school of mathematics that they founded at the University of Chicago. This has led to transformative applications to many areas of analysis like harmonic analysis, ergodic theory, one and several complex variables, partial differential equations, and others. The deep ideas introduced by Calderon and Zygmunt continue being extremely useful in many areas of mathematics to this day. Okay. So our speaker this year is David Jerison from MIT. David obtained his PhD in 1980 at Princeton under the direction of Eli Stein. He was an NSF postdoctoral fellow at Chicago, 1980-81, under the mentorship of Alberto Calderon. And David moved to MIT in 1981 and has remained there ever since. David's work has been widely recognized by several fellowships like the Sloan Fellowship, the Presidential Young Investigator Award, and the Guggenheim Fellowship. He's a fellow of the American Academy of Arts and Sciences and of the AMS. With his collaborator Jack Lee, they were awarded the Bergman Prize of the AMS. David's research is in Fourier analysis and partial differential equations, with highlight works on the Dirichlet problem on the Heisenberg group, the Yamabe problem in CR geometry, potential theory and boundary value problems under optimal regularity conditions, and analogues of the Minkowski problem in differential geometry involving capacity and harmonic measure. Other topics include the study of internal diffusion limited aggregation and questions regarding the regularity, geometry, and topology of free boundaries and minimal surfaces. And these are topics that he will be discussing in these lectures. David.
So thank you very much. Thank you very much, Carlos, for inviting me. This has been a great quarter here at the University of Chicago. Attended just a lot of really wonderful talks in the analysis seminar, the geometry seminar, and the probability seminar. I really appreciate it. And there have been all of these just outstanding special lectures and colloquia. It's an amazing place. I really appreciated being here. I gave my first talk here at Chicago as a postdoc, as Carlos mentioned, in 1980. And the second time I came and gave a talk was at a birthday conference for Alberto Calderon. And so that the first time was in the Zygmunt seminar, before it was called the Calderon-Zygmunt seminar. And second time was in 1995 at a birthday conference for Alberto Calderon. And so now, you may notice that it's 2025, and my dates have formed, the gaps form a geometric progression. So you can look forward to seeing me next in 2185. All right, so I'm going to talk about how level sets of solutions to differential equations, semi-linear differential equations are, I got my shot here. So what I'm talking about today are solutions to equations of this form, which are called semi-linear if this function f is nonlinear. And they're elliptic because this is the Laplace operator on Rn. Okay, but what we're, even when this is a linear problem, the problems that we're going to be considering are nonlinear because they have to do with the level sets. So those are the sets where u is equal to tau. So we'll always assume that the gradient of u is not zero, so that this is a manifold, and locally we're only interested in local behavior. The global behavior will be incredibly important later on, but let's just say that this is the general topic. So I'm going to begin with an example and a question, and then try to set the stage for more complicated things. So the first thing that we'll consider is the ground state eigenfunction. So that's this equation here, right? And it's in some kind of domain, which is sitting inside of Euclidean space, let's say. And it's going to be positive also, which means that it's the ground state. It's the first eigenfunction. Always the first eigenfunction is positive, or at least after multiplication by a constant. It's unique up to a constant multiple. And we're assuming that C is 0 on the boundary. Okay? So the question that I want to ask to start out with here is, what are the shapes of what's the shape of the level sets? Okay? And so let's just draw an example here. Here's a right triangle. And suppose it's n is this dimension here, and 1 is this dimension here. And then you can ask yourself, well, it turns out that it has a unique maximum, which maybe I'll use colors here. Maybe I'll use green for the max, okay? So here's the max. X bar is equal to the max of psi, right? And then the question is, what's the shape when we're halfway up? So it's 0 on the boundary. It's whatever the maximum value is here. And the thing that I'm going to draw next is C of x, the level set a half of the max. All right? So that's this guy here somehow. Looks a little bit like that. And the remark, the observation, which I made in the 1990s, is that the aspect ratio, well, the height is approximately 1. Let's say it's a half or something like that. It's roughly the same, okay? This horizontal distance is very different from n. It's n to the 1/3, okay? And this has to do with the transition region for Bessel functions. You can't quite, this is not an explicit eigenfunction, but you can do it for the circular sector, and you can see immediately what's the right thing. And anything in between n to the 1/3 and n is possible, is the aspect ratio, and the detailed description of what actually goes on is something that you can say universally for all convex domains, okay? All convex planar domains. So this is something that I did in the 90s. And so what I want to do is focus on this most sort of simple-minded question that you can ask about this. The observation, in addition to this, is that after changing shape dramatically for the first half of its life, inside here, it shrinks, of course, to an ellipse, right? I mean, it has to because it's a smooth function, and at its maximum, it's just quadratic locally. So the point is that the aspect ratio just stabilizes after this. It's always for C of x is equal to C x bar, where C is greater than or equal to half. It stabilizes. The aspect ratio the aspect ratio stabilizes. So maybe I should just say stabilizes. Obviously, it shrinks, but it's the same ratio as it goes on. Okay, so let's formulate that in a more systematic way. So first of all, I'm going to generalize very slightly. I'm going to look at eigenvalues with a potential, okay? And I'm going to insist that V is convex, is a convex function, all right? And I'm going to take the ground state, which is this positive eigenfunction. I'm just going to assume that everything is on all of Euclidean space, that the thing spreads out. This actually is a special case because you can let V be equal to, say, 0 inside and infinity outside, and that's a convex function because the triangle is a convex set. So the case of convex bodies is a special case of this, right, in the limit. Right, so this is a slightly more general context. And the remark, so the first, there's a theorem in this subject to begin with, which makes this a coherent question, which is due to, it's Braskamp and Lieb from the 1970s, which says that if you take the Hessian matrix of the logarithm of psi, so psi is positive, so its logarithm makes sense, right? And so I'm going to do this. Now, it should be a bump, right? Well, so I'm going to put a minus sign here. This is positive definite. Okay. And before I go on, let me just mention, this is a qualitative statement. The sharp quantitative statement for convex domains is a beautiful theorem of Andrews and Clutterbuck, which gives rise to estimates for the gap between the first and the second eigenvalue. So the sharp estimates for this is one of the biggest ingredients in their proof to understand the gap between the first and the second eigenvalue. That's a very pretty geometric work. Anyway, this guy here is positive definite, which means that all of the level sets are convex. And it makes perfect sense to ask this question in generality: what do the level sets look like? So the conjecture is the following. It's this stabilization statement, but I'm just going to make it very precise. What it says is that this matrix is bounded between a constant times the value at the max and another constant times the value at the max. Okay, but this, of course, only when you for more than halfway up, right? If this is true. Okay, it stabilizes after we get halfway up. And that's sort of this is the whole story here, I hope. Now, there's one more thing, by the way, which is where the little green dot is. That is how far to the left or right the center is. But in fact, that's just another conjecture, which I'm just not going to state. But anyway, there's a coherent way of asking that question too, exactly where this thing is. And there's, of course, one could ask for more precision than this, but this is the most reasonable thing. Now, so what's the evidence in favor of this? Well, first of all, for planar convex domains, so the important point is this is a dimensional constant independent of V. Okay, it's a universal for all convex potentials. So this is true in dimension 2. It's a theorem of Tom Beck, and I'd already proved it for convex domains in 2 variables, or at least it follows from my estimates from the 90s. So this is true for n equals 2, and it's the theorem of Tom Beck. And the other evidence for it is the harmonic oscillator. Okay, so the harmonic oscillator is the following gadget. I'm going to take the eigenfunction first and then tell you what the differential equation is afterwards. The eigenfunction is the Gaussian. So Q, well, I'm going to write Q2. Let's see. I can't remember what I wanted to say about this. Yeah, I think I want it to be half of the... It's just quadratic. I think I'll divide by 2 for trivial reasons later on. Okay? So this is the eigenfunction. So what's the equation? Well, minus Laplacian plus the gradient of Q squared. This is the potential. It's convex because it's a quadratic. Okay, C is equal to the trace of the matrix here times C. Okay. So this is just true in total generality. And now let's take a look. What happens if we calculate m of x? All right. it's the Hessian minus the Hessian of e to the minus q, right? Which, whoops, there's a very important thing which I left out here. What did I,
over there.
Good. Let's see here. There's a logarithm, yes, here.
It's not easy.
Yeah, right, that makes this computation less messy. Okay, so of course this is just the Hessian of minus the Hessian of q, which is Aij, the matrix Aij. It's constant, okay? So yeah, this is true everywhere, not just halfway up. And this also indicates a serious possibility that the dimension, it's a dimension independent thing. So it's also possible, maybe, that Cn it is actually, you can see, independent of dimension. And what we're saying here is that the ground state has a hidden Gaussian inside of it, a hidden and that the general potential, you know, the harmonic oscillator is just quadratics here. That's the general situation, and we're just saying that all such operators have a hidden harmonic oscillator inside of them.
So you have boundary conditions.
I don't need boundary condition. Well, I mean, so this is an eigenfunction. So say you can normalize its and I don't want, I want V to go to infinity at infinity so that there is a bound state.
But just a convexity assumption?
Yeah, convexity plus that it goes to infinity. In other words, so in other words, it's sitting in, this is a potential well. It's sitting inside of a well. I'm sorry, I'm being a little bit cavalier about what the actual hypotheses are here, but they're totally modest and reasonable. Okay, so this is a question, and I don't know the answer to this question. There's another case for which it's true and for which is dimension independent, which is when V of x is a product of one variable. Then it essentially falls from the one-dimensional form in this case. Okay, so that's a question. And now I want to tell you about how I came to connect the shapes of these level lines or level surfaces of eigenfunctions to problems in differential geometry. Okay, what the link is. Okay, so this comes from something that I'm going to call the Klartag analogy. So Boas Klartag made this observation in 2018. So the level set flow. No, I'm jumping the gun here. So the nodal set, this is what he actually said, the nodal set of an eigenfunction is stationary for flux in the same way just as minimal surfaces are stationary for area. Okay? So this is a remark which he made, a side remark in a talk he gave in 2018, and I happened to be there, and I said, hey, what about the other level sets? And it turns out that if you just check the arithmetic, the other level sets decrease flux fastest in the same way that mean curvature flow decreases surface area fastest. So that's an identity, and I'll write down our first variation calculation. And let me write down what that is. So first of all, let me remind you, and not only that, but it actually applies to this general situation here. The special case of eigenfunctions is the case, it is this, right? Okay, but it applies in complete generality, so it's a very general statement. So what does it say? It's the following statement. So suppose you take the level set, okay? That's I defined that over. Well, it's up on that board. Let's just remind you, it's always going to be this level set here, okay? And then the idea is now we're going to be varying tau, okay? So we have this level set, and now we're going to try to move it. And the way we move it is we take another parameter t, and we take an amount, a normal variation of the thing. We move it in that direction by some functional factor. So v can be any function. So in other words, we're taking the thing and we're varying it in various amounts according to v. This is the standard, what we do when we do first variations. Now, what are we varying? We're varying the flux, which is this gadget here. It's the length of the gradient times the surface area. That's what the flux is. Okay? It's also equal to the normal derivative through the level surface, which is how fast the gradient field of u would move. All right? So that's called the flux. And we take the derivative of that with respect to this parameter t here, and we evaluate it at t equals 0. Okay, and that's called the first variation. And the formula for it turns out to be v tau. Oh, whoops. Yeah, I don't seem to be able to. So this is f of tau. The factor f of tau occurs times v times d sigma. That's what turns out to be the formula. All right? Very simple formula. So why does that show that the fastest way to decrease this gadget is to go by the level set flow? Well, the answer is that what we should be doing, if you think of this number as being negative, all right, then what I need is the maximum of the rate of change, right? Subject to what? Well, by analogy with surface area, it should be subject to v squared gradient u d sigma is equal to 1. This is the constraint that you want. All right? So this is the correct analogy with what happens with mean curvature flow, where, by the way, there's a factor of h, the mean curvature, when you do this. Okay, so this is the idea. And now, what happens with this maximization problem? The answer is that v splits the difference. The correct answer is v is equal to a constant divided by the grad u. That's what it should be. This is the Lagrange multiplier, and this is the factor. So that 1 over grad u here, and then here 1 over grad u squared cancels with this grad u. So that makes these two terms a tie. This is what always happens with the arithmetic in these kinds of problems where you have a linear and quadratic constraint and a linear objective function. Okay, so this is true, and this is level set flow. Dx d tau equals 1 over grad u times the normal is level set flow. Okay, I remind you that dx by dt equals h and is mean curvature flow. And completely analogous. Right? So this leads one to think about the following idea. So let me go back to my picture here. So here are the level sets. And I'm going to tell you a story. The story is not quite right, but I'm going to tell you a story anyway. So the story is the following. Here's a progression here, which is extremely reminiscent of what are called shrinkers in mean curvature flow. The shrinkers go to the sphere. And here we're starting at 0, that level set, and we're shrinking down. We're shrinking to an ellipse, but still, we're shrinking to something, and it's getting more and more clean. It's getting nicer and nicer as we go to the singularity. And kaboom. And in fact, the singularity is just what we think. It's where the gradient vanishes. All right? So that's where, of course, everything goes wrong. The flow doesn't make any sense anymore. So this is all perfectly sensible. And there's actually a theorem in this subject, which is a pinching theorem due to Hamilton, which says that for mean curvature flow, the curvatures get closer and closer together. And eventually it becomes closer and closer to a round sphere. So it seems like maybe we're in such a situation. Now, that turns out to be, after much thought, that turns out to be wrong. But it's sort of kind of almost right. So what's the matter with this is that the mean curvature flow is a parabolic equation. And here we have an elliptic equation. So what's really happening here, actually, is that the level sets are shapes which are like geodesics. And they've got a starting place, which is the outer boundary, and an ending place, which is the little green dot in the middle. And they're the ones in between. And the reason why the ones halfway start to resemble what's in the middle is we already know what's on the outside, which is it's already convex. And we already know what's in the inside, which is exactly the ellipse, infinitesimally. And so halfway, it's sort of like the left-hand endpoint. So it's more like a geodesic where we know the endpoint. So the difference with the parabolic equations is you start with initial conditions, and that just determines where you're going to end up. Here, we don't know where we're going to end up, but we actually do. We know what the behavior is at this place. So we're okay with having that. And of course, the equation is going to be second order, not first order. Now, from the point of view of differential geometry, what we're really saying is the following. What we're really saying is that we should look at all these surfaces and then differentiate the hell out of them, because that's what you do in differential geometry. You want to see what happens. And so in mean curvature flow, the first thing you do is you differentiate the first fundamental form, right? And you get minus twice h times the second fundamental form when you do the evolution. So the evolution of this is this. So Aij is the second fundamental form. That's the matrix of curvatures of the surface, and then the trace of this is equal to this h. That's the mean curvature. So this is the second fundamental form. And this is the mean curvature. Technically it's the sum of the curvatures rather than the sum divided by the dimension. It's what's called mean curvature these days. Anyway, so this is the equation for the evolution of the restriction of the metric to the surface. And then you keep on doing this differentiation, and you get a formula for this guy. And it turns out that this has a super interesting formula, which was derived by Huisken. And then Hamilton discovered how to think about this formula much more invariantly. And that's what we're going to need in order to think about our formulas. So we've gotten started. And let me just tell you from an invariant point of view what the differential equation is. In invariant formulation, this flux has a fancier way of being written, which is that it's the interior product of the gradient with the volume element. Okay, and that's the same thing as the Hodge star of the exterior derivative of u. Okay, so this is the flux is a really natural object, and it comes up in differential geometry. And the formula that actually governs this whole thing, which is essentially, so you take the gradient divided by the gradient squared. That's a vector field, and you take the Lie derivative of this n-1 form here, and it's equal to a multiple of itself always for all level sets, for all scalar functions u. And the multiple is exactly Laplacian u divided by grad u squared times star u. Okay? So this is the equation which is equivalent to the variational formula that's written on this other slide, on this other here. And this is the first step in just differentiating the hell out of these things and just seeing where they go and when the equations close, which is what you do in differential geometry to understand what's happening. All right, so this is a clue that there's going to be nice things that happen. And of course, it's cleanest when the Laplacian of u is equal to 0. That was the case, the nodal case. That was Clartot's first case. That's the case where you're on the nodal set. So f of u is equal to 0. So the right-hand side is 0. All right. So that's the clue that there's something going on here. And then the whole rest of the game is to try to figure out whether this has to do with anything. Okay, so now I'm going to back up, and I'm going to tell you the history of the study of level sets, and from a very skewed point of view. All right. I'll start kind of late in the game here, but okay. So here's a little bit of history. So there's a theorem. The way I want to start is there's a theorem which is due to Caffarelli in 1986, and it says the following: if you take a harmonic function. By the way, we're going to be dealing almost exclusively from now on with harmonic functions. It turns out that in all of these subjects, you can sort of put in by hand the right-hand dependence once you understand what all the differential relations are. So if we have a harmonic function in Rn, okay, and the level set u equals 0 is contained in a slab. It's contained between two horizontal things. So it's here, it's trapped between this. Okay. Then u of x is equal to bxn plus c. It's linear. In fact, all of its level sets are planes. Okay. So this turns out to be not obvious how to prove it, okay? And it's the beginning of a giant subject which Caffarelli developed in the 1980s, having to do with free boundary problems, and it applies to just anyway. But this is this sort of Liouville type theorem, the sort of global theorem, which tells you that there's something going on here, and it's extremely nonlinear because you're dealing with the level set of something, even though we solved a linear equation. Okay. So this is the starting place for the theory of all of these semi-linear equations. Now, let me just remind you of this special case. So there's a simple-minded special case which you might recognize. The special case is the special case u of x is equal to bn xn plus a function of the other variables. Okay? Now, if that's the case, then because this has harmonic, this thing is also harmonic. Okay? And then what we're saying is that we have a harmonic function, which is v. Of course, it's one variable down, but that doesn't make any difference. And v is bounded. Right? And now this is the familiar Liouville theorem. This is saying this statement, this implies that v is constant. Okay? Now, So that's sort of, if you like, that's sort of the linear special case of this nonlinear phenomenon. But actually, even this has an interesting nonlinear aspect to it, because the best proof, so there are proofs of this that involve integration by parts and things that exploit linearity. But there's a better proof, which is more quantitative and much deeper and much more important, which uses the Harnack inequality. Okay, so the Harnack inequality is the core of everything that I'm going to talk about in terms of technique, although we'll just be referring to it. The Harnack inequality says the following thing. It's a localized quantitative version of the maximum principle. And what it says is the following. If you have a function which is 0 in a ball of radius 2, and v is positive. So I cheated because I have to shift it up so that, because it's bounded, I have to shift it up so it's positive. But it's the same idea here. So we have two properties here. And I want to make clear that this is true in B2. Both properties are true in B2. All right? Then the ratio of, so if we take 2 points, P and Q, which are in B1, then the ratio of V of P to V of Q is bounded above and below by a dimensional constant. Okay? The upper bound and the lower bound are symmetric because I didn't tell you which one was P and which one was Q. All right, so this is the Harnack inequality. And I want to, let's write it in a strange form, okay, so that we see exactly how to connect it to the subsequent properties that I'm going to describe here. So first of all, the hypothesis is really that log V is between infinity and minus infinity on B2. Okay, it's well defined on B2. And the conclusion is that the logarithm is bounded. On B1. Okay, so a qualitative property gave us a quantitative property, and the amount of the oscillation, well, maybe I should put it this way, the oscillation of a logarithm of B is bounded by an absolute constant independent of the function, just a dimensional constant. Not the same one as over there. Okay. So from the point of view of history, the way that Caffarelli used this, maybe I'll trade boards and I'll just, I think I'm going to get rid of this over here because it's part of the same idea. So the way that this gets used when you're looking at equations like this is that you take the derivative with respect to the xn direction of this guy. And then in disguise, what's happening, although this really has to be interpreted carefully, is that sort of on average or usually or just sort of this thing is positive. Okay? And then you can apply the Harnack inequality to this guy. And that's where the nonlinear problem, where you can replace the linear problem by the nonlinear problem. And this all has to do with applying versions of the maximum principle, very interesting, amazing versions of the maximum principle. I mean, this is work for which Caffarelli just won the Nobel Prize. I mean, this is a really big deal, but so I can't do it justice. But anyway, this is morally speaking what's going on. And the part of it that I want to carry on to the next step is just the statement that we're talking about directional derivatives. Okay, so the next step in this process to explain the history is to explain how the geometers look at this kind of thing. And the way geometers look at it, is they have sharper inequalities called differential Harnack inequalities. And they're a little bit more specialized and much stronger in certain ways. So let me describe this. I think I probably want to keep this picture, but maybe not. We'll see. Okay, so the first such theorem is this Li-Yau differential Harnack inequality. I'm going to tell you a baby version, because we don't need anything more than that. Just the absolute simplest version, which is the following. You take the solution to the heat equation on all of Euclidean space. Okay. And then you ask yourself, you take 2 points in space-time. So here's x1, sorry, maybe I'll call it P and Q. All right, so here we have P and Q. These are these points in space-time. And you ask yourself, what's the largest that U of P divided by U of Q can be? Okay? And this is assuming that, I'm sorry, there's one more key assumption. I'm assuming that U is positive. Okay? So the point is that this is achieved. And it's achieved by the simplest possible mechanism. Namely, I'm going to draw this line back to here. Okay, and here I have my green delta function here, green being supposed to be corresponding to what I had this other singularity here. Okay, so I go back here, and what I use is the Gaussian, the solution to the heat equation, which starts with the delta function here. And morally speaking, you can kind of see that this one should make P the largest relative to Q, right? Because it's sort of in the way. Right? Because P is in the way of Q. You could think that. And not only is this sharp, so this is an exact equality everywhere in all directions, but that means that you can do the infinitesimal. That is, you can fix Q, and you can move P towards Q, and you can take the derivative in that direction, and you get the optimal bound for the infinitesimal. So this is why I talked about directional derivatives. This gives you the best space-time directional derivative bound. For log U. It's the ratios of the functions that are at issue here. So when we're talking about that, so infinitesimally, it's the derivative of the log. That's what's involved. Okay, so this is what this thing says.
So your picture is already in Rn cross R plus?
That's right. This flat line is in Rn minus n minus 1, and the t direction is the vertical direction. This is the t variable, and this is all of the x variables. Thank you for the question. Now, it's very important that this is a global result. This is wildly false if the thing is only defined on part of the domain, if it's on some little chunk. It has to do with the fact that Rn is complete. The more general theorem of Li and Yao is on manifolds with reaching non-negative in this particular, the way it's stated here. But it requires that the manifold be complete and that the solution is entire. It's very much a Liouville type theorem. It's not a theorem about a localized theorem. Okay. Anyway, this is the idea. Now, there's something that is very important here, which I want to point out in addition, which is weird and that you should be wondering about if you actually look at this very closely. It took me probably at least a decade to realize after reading this thing that there's something weird about this theorem. So here's what's weird about this theorem. Space-time directional derivative. Seems like a very modest thing to be weird. Why should that be weird? Well, the space-time directional derivatives are derivatives in space plus derivatives in time. But the homogeneity of the parabolic equation has parabolas. It doesn't make any sense that you should be differentiating with respect to t and with respect to x with equal weight. It doesn't make any sense, right? So actually, this line here, which is a straight line in xt space, violates homogeneity of the parabolic equation, okay, which is extremely strange until you realize that actually, if you just base things at delta and you do these straight lines, then the parabolic dilations do preserve this affine shape here. This little splay here is preserved by the symmetries of the problem. So it's relative to delta that this is true, and we've revealed something different about the heat equation, which is that globally it sees straight lines in space-time. Okay? There's a different affine structure which is present in the heat equation, which you cannot see from anything but global considerations. Okay? So that's the object which then gets transplanted and eventually solves the uniformization in the geometrization theorem of Perelman. This is the mechanism that we're going to see is the one that works, and it's the one that I'm looking for in my problem. It's this guy here. It's the connections of causality between the various level sets. When level sets in these nonlinear problems, in all these free boundary problems, the problems of Caffarelli, they talk to each other. The fact that you know that one level set, I just told you that when one level set is kind of flat, it straightens itself out. It obeys its barriers, and in fact, it flattens itself out. And then it tells all the other level sets how to straighten themselves out. They're all planes. Okay? And this level of communication between them is mediated by things like Harnack inequalities. But the Harnack inequalities are extremely subtle. And this is what we're trying to discover, is what the skein of the thread is. And this is going to be mediated by affine connections, by what's the right notion of straight lines in the subject. Okay, so this is what we're eventually going to see. I'm not going to be able to get to all of these points today, but I'm going to try to get you as close as we can to what the big picture is. So it's a replacement for causality. You know, we're very familiar with it, that characteristics in hyperbolic equations have causality. But it turns out that in these global interesting settings, parabolic and elliptic equations also have some kind of communication and some kind of very sharp communication that's going on between different level surfaces. Okay. I guess we'll just leave it this way. There's no point to trading these guys. Okay, so what's next? What's next is understanding how these sharp inequalities relate to curvature. So I told you that somehow it should relate to mean curvature flow, and the next thing that happened after Liao did these things in '86 was that Hamilton observed that there were some directional derivative estimates for mean curvature, H, in mean curvature flow. So what he recognized is that there's space-time. So this is Hamilton's work from the early 90s. So the early 1990s, Hamilton studied mean curvature flow, which, by the way, on the level of, as I just said, on the level of the metric, it does this, and then there's also this Ricci flow, which looks formally somewhat similar, where this is the metric and this is the Ricci tensor. All right, so there's things for both of these types of flows, and what he did. I'm supposed to step on this thing to make sure the camera goes over. It's having a little trouble with that. Okay, so what he did is the following. He proved space-time derivative estimates for H and the scalar curvature, which is the trace of this. And the thing that's remarkable about these is they involve not just the directional derivative of H, but also the curvatures. So they're of the form. It's roughly speaking this. I think I'm going to get this right. It looks like this. Okay. So they're estimates for this object here, which is a directional. So sorry. Let me see if I can spread it out so that you can actually read it. So for any vector v, space-like vector v, okay? So in the x directions, if you like, or the directions along the surface. And this is the gradient in the surface direction, okay? This is one of those directional derivatives, but there's a correction which turns out to be fantastic, which is related to the curvature of the surface. And so, in fact, you get information about all of them simultaneously. You track what's happening to the curvature and so on. So this satisfies some kind of maximum principle, and so it's always non-negative. When you start out with a convex, when it starts convex, it continues to be convex, and there's control over the curvatures. Okay, so this is what Hamilton discovered. And he called them matrix Harnack inequalities because they simultaneously control all of the eigenvalues of the matrix, of the symmetric matrix. So the next thing that happened is, so he did this for both the mean curvature equation and for the Ricci flow. And the formulas that he was using were complicated. And they were complicated to understand. And he and Nolan Wallach noticed a pattern that indicated how you could sort of guess more easily in advance what the formula looks like, which will be very important for us as well. So the next thing that happened is that in 1995, Chow and Chu in 1995 gave a geometric description of what the formulas that very jazzy formulas that Hamilton had cooked up mean. And what's going on is the following. So starting from the Ricci flow equation, which is this equation here, the first thing they did is they built a metric G tilde on space-time. Okay, they built a metric G tilde on space-time, which just depends on the scalar curvature. So it depends on two derivatives of the metric. And then what they did was they discovered that his jazziest formula was just what happens to the heat equation for this new metric here, acting on its curvature. You have to raise and lower indices correctly. And then there's an amazing formula for this. Let's call these different indices just in order to indicate that where there's not supposed to be a relationship. It's that the Q tilde has these four indices, and then there are four more indices over there. Right? So this thing is some quadratic expression. So this is where the differential equation closes. And this is an unbelievably complicated gadget. Notice that G tilde depends on two derivatives of the metric. So that means this depends on four derivatives of the metric, and we're differentiating two more times. So this depends on six derivatives of G. All right, and this is the formula that gives everything. Are we done?
Quite, but soon.
Okay, all right. So I'm going to be okay. So I'm never going to. Okay, so good. Thank you for warning me. So let me I'll wrap it up right now. So the next step is Perelman's work, and this is in 2002. In which he resolved the geometrization conjecture and the Poincare conjecture in 3D. And in this work, what he observed is that the affine connection of G tilde is the key to the subject. Okay? The straight lines determined by this G tilde are what we want to understand. And let me draw the picture over here from my original picture. What's really happening is that Ricci flow is going this way, and we're going that way, and this is Ricci flow encountering a singularity. Okay? And then what you do is you follow the geodesics of G tilde backwards. And this gives you all the differential inequalities that you want. So this is the geometry. So there's a Li-Yau inequality. There's all this stuff that's the same, but and some fancier things having to do with volume comparison. Okay, so this is what happened in this subject in this time. Now, what we're trying to do, and which I will try to describe to you in some detail next time, is the same thing over here. Okay, for level sets of eigenfunctions and harmonic functions. Now, so there's a lot that's better, which is that there's no problem with existence theory. This is trivial. We already know that the functions are there and that the whole flow is there. And we even know when we encounter singularity, what the singularity is. We know everything about that. What we don't know is the relationships between them, the inequalities between them. And we also, of course, don't know what G tilde is. Now, unfortunately, G tilde depends on three derivatives of U, not two. And so the actual ending equation is going to depend on 7 derivatives of U. So this is really complicated, and it involves some algebraic geometry. So I will, unfortunately, have to say that essentially just on elliptic curves and hyperelliptic curves. So I will have to save that for next time. Okay.
Any quick questions?
Yeah, sorry about that. I realize now that I should have been paying more attention to the time. Thought I was going to get about twice as far.
Well, if not, we'll save the questions for next time.
Thank you, sir.